Namaskar and welcome to this special session under the celebration of Azadi Ka Amrit Mahotsav. First of all, I would like everyone who have joined us, first and foremost, today's special guest and invited speaker, Dr. R. Krishnan, scientist. Just a moment, there is some echo, I think. Sorry for the interruption. There was some echo coming to me. Yeah. So first of all, I welcome today's special guest and invited speaker, Dr. R. Krishnan, Scientist G and Acting Director, IITM, Pune, Dr. Mukhopadhyay, Dr. Milind Majumdar ji, Mrs. Das from IITM, Professor Arga Banerjee, and Dr. Joy Montero, the Chair, Earth and Climate Science, IISER Pune, entire IITM faculty, entire IISER Pune faculty, and viewers who have joined us from outside IITM and IISER family. You are all most welcome to this very special joint seminar by IISER Pune and IITM Pune. First of all, let's talk about why we are having this celebration. You know, you are all aware that India, government of India and entire nation is going through, a mega celebration, Azadi Ka Amrit Mahotsav, where we are celebrating and commemorating our 75 years of independence. And this very celebration is dedicated to the people of the nation, their contributions so far, and how we are going through, different developmental phases, what are the challenges and how we can move ahead, the way forward. In this direction, IITM is also contributing by organizing special lectures under the area of, weather and climate sciences. We try to highlight India's, achievements in weather and climate sciences through all these years, wherein we select specific topics and talk about these topics, especially in Hindi and regional language Marathi, so that we reach to the masses. Today's lecture would rather be in English by Dr. Krishnan. So, as you know, that this year's Nobel Prize went to one Professor Sekiro Manabe for his groundbreaking contributions to climate sciences. It is a great matter of celebration and pride for the weather and climate fraternity, because this gives much needed attention to weather and climate sciences, how weather and climate sciences are important for us in this climate changing and global warming scenario. So Professor Manabe's contribution in this area is very important. It is seen as a a breakthrough which highlights weather and climate's contributions in social development and social welfare. And today, Dr. Krishnan will be talking about Professor Manabe's breakthrough contribution in climate sciences and how he could achieve all that and how that is important for us and how we can move forward. Dr. Krishnan is a well-known personality in climate and climate change sciences globally. He doesn't need any introduction, especially when weather and climate sciences fraternity is concerned. But we have viewers, from other area. So I would like Professor Joy Montero from IISER Pune to formally introduce today's special guest to our viewers. Dr. Joy, please.
Thank you, Dr. Abhay. Hello, everyone. Welcome to this very special seminar, which is going to look at and examine the contributions of one of the Nobel laureates this year. I think today's speaker, Dr. Krishnan Raghavan, is probably most suited than most people in India to be giving this lecture. This is because of a couple of reasons. One, as the Executive Director of the Center for Climate Change Research here at the Indian Institute of Tropical Meteorology, his group has been leading India's efforts in developing an Earth system model for climate change studies, as well as contributing to various climate change policy reports, which I will come to. And secondly, on a personal level, he has actually worked with Dr. Manabe in Japan during his postdoc. and therefore he not only knows the science, but he also knows the person very well. And I think such a combination is rare to find, and we are very glad to have Dr. Krishnan here. So just to give you a brief introduction to Dr. Krishnan, his area of research has been in climate modeling studies with a particular focus on climate change, Asian monsoon, and the water cycle. As I mentioned, he's the head of the Center for Climate Change Research here at IITM Pune. And his team at CCCR has developed the first global climate model from India, which has contributed to the IPCC sixth assessment report. He was very actively involved in the IPCC activities. He's the coordinating lead author of the Working Group 1 report, especially the one chapter which deals with water cycle changes. And he's also the drafting author for the summary for policymakers. And his team also published the first national climate change assessment report in India as from the Ministry of Earth Sciences last year. He studied applied mathematics for his master's from the Madras Institute of Technology in Chennai. And he did his PhD in atmospheric sciences from the famous Physical Research Labs, Ahmedabad. He got his degree, and then he has been working with IITM since nearly now 20 years almost. A little more than 20 years, I'm sorry. And he has published a large number of papers, 140 of them, and he has supervised or co-supervised many PhD students as well as master students. And he has also been, his work has been recognized across many fora. He's the fellow of both Science Academies of India, the Indian National Science Academy and the Indian Academy of Sciences. And he's also the fellow of the Indian Met Society. And he was recently awarded the National Award for Excellence in Atmospheric Science and Technology by the Ministry of Earth Sciences. And these are just some of his many laurels, and one can go on and on. But without much more ado, I would like to invite Dr. Krishnan to start his lecture, and hopefully we will leave this lecture with a much better appreciation of why the Nobel Prize was awarded in the field of climate science, which is very unusual, as well as some insights into the person himself, Dr. Suki Manabe. Thanks, everyone, and over to you, Dr. Krishnan.
Thank you, Dr. Joy Montero and Abhay Singh, Partha, Milind, and all colleagues. Good afternoon to all of you. Just a minute. Can you see the screen? Hello.
Yes, sir. Yes, sir. Visible.
Yeah. Okay. Yeah. So good afternoon, everyone. On this important occasion of the Azadi Ka Amrit Mahotsav, to celebrate 75 glorious years of India's independence, it is a great privilege and honor for me to talk about the groundbreaking contributions of Professor Sukuro Manabe in the field of climate science. Professor Manabe is a climate scientist par excellence. In addition, he inspired and mentored generations of climate scientists across the world, as well as several Indian scientists, including myself. My scientific interactions with Professor Manabe at the Frontier Research System for Global Change during 1998-2000, when I was a visiting researcher there, have greatly influenced and inspired the research and development activities at the Center for Climate Change Research, Indian Institute of Tropical Meteorology, Pune, most important being the development of the first global change climate projections from India using the IITM Earth
Excuse
system.
me, Dr. Krishna, sir.
Yeah.
Sorry for interruption. Actually, PPT is not visible. Can you stop sharing and reshare it, please?
Yeah, I've not gone to the. I've not gone to the second slide. I'm just starting.
No, it's coming blank, sir.
Oh, it's coming blank. Okay.
Yeah, please.
Yeah, just a minute.
Yeah, sure, sir.
Yeah, I'll complete this sentence. Most important being the development of the first global climate change projections from India using the IITM Earth system model and the contributions to the recent IPCC AR6 report. Yeah, let me now stop and again go back. Is it now visible? Hello?
Yes, sir, visible. Yeah.
Okay. Yeah. So today's talk, I will be talking about, this is basically paying tribute to Professor Suki Manabe for his groundbreaking contributions to climate science. So this year's Nobel Prize in Physics 2021, it went for 3 people, Professor Suki Manabe, Professor Klaus Hasselmann and Giorgio Parisi for groundbreaking contributions to our understanding of complex physical systems. In particular, the climate science prize was shared by Professor Manabe and Professor Hasselmann for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming.
Dr. Krishna, sorry again for the interruption. Again, it's not coming, sir.
Oh my God. Okay. You are not seeing this slide?
Yes, sir. Not
now.
Not yet.
Dr. Krishnan, the third option might work better. The book type of icon instead of the.
Okay. Book may work better, is it?
Yeah. Yes.
Is it okay now?
Yes. And if you could minimize that Teams screen, it's visible.
Black menu.
Yes.
Yeah. Fine. Yeah.
Thank you.
Yeah. Now can we just?
Can we check whether YouTube it is coming properly? People.
Yeah. Now it's coming, sir. Yeah.
Now it's coming. Okay.
Yeah. YouTube. Now it's on. Yeah. Thank you, sir. Sorry for the interruption, sir.
Yeah. I'm sorry.
Now it's okay.
Yeah. So this year's Nobel Prize in Physics was shared by 3 scientists, eminent scientists, Professor Sukuro Manabe and Professor Klaus Hasselmann for climate science, and Giorgio Parisi for working on complex physical systems for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. In particular, for the climate science, the prize was shared by Professor Manabe and Hasselmann for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. So here I want to draw attention to Professor Manabe's climate model. Manabe was the first researcher to explore the interaction between radiation balance and the vertical transport of air masses due to convection, also taking into account the heat contributed by water cycle. This is what is known as the radiative convective model, which was a groundbreaking work where he demonstrated the effect of how increasing carbon dioxide concentration in the atmosphere could increase the surface temperature of the planet. And I will come to those details in my subsequent slides. Professor Hasselmann identified fingerprints in the climate. He developed methods for distinguishing between natural and human causes of atmospheric heating. Basically, this work is important for detection and attribution of climate change. And about Professor Manabe, he is, as I said, a climate scientist par excellence, pioneered physical modeling of Earth's climate and global climate change research, created and led a world-class climate modeling group at Geophysical Fluid Dynamics Lab, GFDL as we call it, Princeton, USA. He made several landmark contributions on a wide range of climate topics. The most important one which I will be talking today, the elucidation of the atmospheric radiative convective equilibrium with positive feedback effect of water vapor, the famous paper by Manabe and Weatherald in 1967. He also contributed to several other landmark contributions, such as the development of a three-dimensional models of atmosphere for climate studies, quantified the effect of increasing atmospheric carbon dioxide on the Earth's climate, simulated for the first time the three-dimensional response of temperature and hydrological cycle to increased carbon dioxide, first simulations of climate by a coupled ocean atmosphere model in 1969 with Kirk Bryan, important contributions on modeling of the South Asian monsoon. He also investigated the effects of orography on climates in different regions of the world, numerical modeling of the effects of soil moisture, variability and land surface processes on climate, modeled the influence of ocean atmosphere coupled variability on different time scales, investigated the time dependent response of climate to changing atmospheric GHG concentration, what we call as a transient experiment. And he also worked on past climate changes, modeling of past climatic changes like the Ice Age and the role of freshwater input into the North Atlantic Ocean and abrupt climate change. So there are many more. I am unable to just list them. So when you see the range of topics, it's really wide range of topics, and it's a very, very visionary thinking. So he's a very, very visionary scientist that we can clearly see. And it's clearly impossible for anyone to summarize all this in a 1 hour lecture. So I will try to do as much as possible, focus on some of the topics that have been mentioned here. And based on my personal interactions, I have seen his scientific approach. The emphasis is mostly on understanding the climate phenomena. He laid lot of emphasis to understand what is the climatic phenomena, why it is happening. Understanding was the primary importance. Also, the physical processes of variability and change. Told it's very important to understand what are the physical mechanisms, why the variability is happening, why the change is happening. And also his approach was very simple, clear and practical. He always emphasized it should be your approach to understand a proposed hypothesis should be very simple, and it should be easily understandable and reproducible. And it should be quantitative and straightforward. And lastly, he also emphasized that one needs logical and deductive reasoning. You should go step by step, deduce why this is happening. The deductive reasoning is something which he laid a lot of emphasis. And these are some of things I learned from him. Of course, as a human being, very, very inspiring person, positive energy, full of positive energy and enthusiasm, very cheerful and very helpful, and can never forget those days. And so he guided and mentored generations of climate scientists across the globe, several Indian scientists, and truly is a great hero. He's been my greatest hero, I would say, and a great visionary scientist. Yeah, so this is a small YouTube link of his audio. This is not a video link, this is an audio link. I'll just play it.
Dr. Krishnan, it's not audible. We're sorry.
Audio is not coming.
Oh, it's not audible?
No.
Okay, just a minute, please. This.
Go to audio again, share the audio. Go back.
Go back, I have to come back, is it?
Come back, yes, there only, yes. Then, no, this one. Yes, now share the audio, include the audio system, yes. Go here, yes, yeah.
My name is Adam Smith from Nobel Prize.
Is it audible now?
Is it possible, please, to speak briefly with Professor Manabe?
Yes.
Oh, just a second.
Thank you.
Hello.
Hello, yes. Many congratulations on the award of the Nobel Prize.
Oh, thank you.
There's much excitement downstairs, I can hear. Everybody's very happy.
Yeah. I never thought that I received Nobel Physics Prize for the work I have done a long time, which I enjoyed very much. But I has been doing science of climate change. And when I look at all these four distinguished recipients, nobody received physics prize for my kind of work. And I really appreciate that the Swedish Academy of Science to choose this field, topics of climate change, which I enjoyed very much to do throughout my linguistic career, which lasts more than 60 years. And so I am so surprised, but at the same time, I really appreciate that Swedish Academy of Science chose my research for this honor of this year.
I suppose they want to show how important a fundamental scientific understanding of the climate is.
That's right. Yeah. I think this one of the important things is understanding climate change. And what I did was using climate model which I constructed, changing one thing at a time, and just like a chemistry, do a chemistry experiment.
Yes.
I made a numerical experiment using this model, changing one thing at a time, thereby understanding how climate system works and how temperature change, how rainfall change, and why these changes result in the massive flooding which has been occurring near Beijing and in Japan, and all these massive flooding, and how this very frequent drought has been occurring all over the world. And I try to understand it using a climate model, why this is happening. I think most important thing is understanding climate change. The prediction of climate change without accompanied understanding of it is saying no better than prediction of fortune teller.
Such an important topic, such an important problem.
Yeah.
And almost everybody agrees about the importance of it. But tell me, why did you begin to be interested in meteorology and the climate in the first place? What drew you to the subject when you were young?
Yeah, it was, I went to graduate school of University Tokyo. Then this graduate school of geophysics, I decided to focus on meteorology. At that time, the weather forecasting
Yes.
was more of arts rather than science. Look at the past weather map and make
Yes.
forecast based upon the sort of hunch and experience. But at that time, at Institute of Advanced Study. Von Neumann, who is a pioneer of computers, among many other things, decided to do weather forecasting based upon laws of physics, which is a hydrodynamical equation, right? And so he started small groups and started studying weather forecasting. And this is the beginning of daily weather forecasting, which has become indispensable for our daily life.
Over your career, you've seen weather forecasting and climate prediction change from art to science. Amazing.
Yeah.
It's been a pleasure to talk to you, and my congratulations.
Hi. Hello.
Hello, it's Adam here.
Okay. Thank you.
Thank you.
Yeah.
Yeah. So I'll continue with my talk. Are you able to see the next slide, please? Hello?
Not yet, sir.
Oh.
Yeah. Yes,
you can
visible.
Yeah. So, so basically the audio which I played, so he emphasized that understanding climate change is very important. Any prediction without understanding is as good as what a fortune teller would tell. So the same thing he used to repeat when he used to say when I was there in Frontier more than 20 years ago, that understanding is very, very important. So that is one point I want to just mention. And so briefly, I will give a short history of numerical weather prediction and the science of climate change in my next two slides before going into the topic itself. Numerical weather prediction, or NWP, the basic ideas were developed more than a century ago. Wilhelm Bjerknes in Norway in 1904, he proposed that weather prediction should be based on well-established laws of physics and regarded this as a deterministic problem. And so his view was that if you have a sufficiently accurate knowledge of the atmospheric initial state, it should be possible to predict future states. And subsequently, 1922, L.F. Richardson from UK. So this was during the World War I. He attempted to solve these equations numerically by hand. Unfortunately, the solutions was a failure. And this was due to some other reasons, which was later realized. Several obstacles had to be overcome first. Fuller understanding of the atmospheric dynamics, and meanwhile regular radio sondes and other satellites, they provided the initial conditions. Basically, the NWP, the numerical weather prediction, is an initial value problem. It heavily depends on the initial conditions. And stable finite difference schemes were developed for this finding numerical solutions. And one of the important...
Dr. Krishnan.
Hello?
Yeah, sorry for interruption. Can you minimize the Teams menu, please?
Teams?
It's actually hiding some portion of the screen.
Okay, fine.
Yeah, thank you.
Yeah, thank you. Yeah, so so during this time, as the ENIAC computer, this was the first electronic numerical integrator in computer. This was at the University of Pennsylvania, and as Professor Manabe was mentioning, this came at that time in the late 40s. And there was an important contribution by Jules Charney, von Neumann, and Fjordhoff. They performed a numerical integration of a barotropic vorticity equation, which is a simple, it's a quasi-geostrophic approximation with hydrostatic balance. And they found that this simple system could eliminate acoustic and gravity waves, but still retain the planetary long waves. And this was the problem that Richardson, he was unable to eliminate the gravity waves, which was one of the reasons for his failure of which he made 30 years before that. So the first successful numerical model was of the atmosphere was constructed by Charney, Neumann, and Fjordhoff by integration of this barotropic vorticity equation. Subsequently, Rossby and team 1950, they produced their first successful real-time weather forecast. And by 1956, Norman Phillips developed the first general circulation model of the atmosphere, a numerical experiment. He depicted monthly and seasonal patterns of circulation in the troposphere. And this was the beginning of the general circulation models and climate models. And later, GFDL pioneered this. They took the climate modeling to a different level, thanks to Professor Manabe, Kurt Bryan, and that whole team. And during this time, there was also an important, by 1963, Edward Lorenz, he discovered deterministic chaos. He suggested that a simple model, he had a very simple model of convection, using 3 variables, but it was a nonlinear system. And this simple model, it showed 2 regimes with chaotic transitions between them. So what he proposed was, even if you have a perfect model and perfect initial, almost perfect initial conditions, the forecast will lose skill in a finite time interval. There's an example, a butterfly flap in Brazil can change the forecast in Texas in 1 or 2 weeks. So basically his work showed that there is limits to predictability of weather. And so this was one of the challenges. So weather prediction, there is a so it is not a deterministic problem especially when the time scale extends. It becomes you may need multiple ensembles especially. And so you have to keep this in mind. So when we are talking about climate change, we are talking about a change in temperature due to greenhouse gases. How do we detect them? So it becomes really a challenge because there is so much of natural internal variability within the system. And so this we have to keep in mind in the context of what Professor Manabe and another team did in advancing the science of climate change. And over the period of time, powerful electronic computers, they provided the means of carrying the massive calculations required. And there was a massive increase in computing power during the last few decades. This is a brief history. And now coming to the science of climate change itself, about 200 years ago, Joseph Fourier, he's a French physicist, he proposed that he had proposed what is known as the glass bowl effect. He studied what is the energy balance between the incoming solar radiation at the ground and the radiation that is radiated by the ground. And he tried to understand this, and he roughly understood that the atmosphere should be absorbing the terrestrial radiation emitted by the long wave radiation emitted by the Earth. And this is important for maintaining the temperature of the planet. And this was subsequently studied by John Tyndall in 1859. And Svante Arrhenius in 1896, he tried to quantify the change in surface temperature to be expected from doubling of carbon dioxide. He suggested that if we double the carbon dioxide, how much the temperature would change, surface temperature. He estimated it around 5 to 6 degrees, which was much higher. And subsequently this problem was, and also Guy Callender, he states that human activities lead to increased surface temperatures. And then there were observations of carbon dioxide first it started from Scripps Institute and later at Mauna Loa facility in Hawaii for the detection of atmospheric composition. And this was by Charles Keeling. Now they clearly documented how the carbon dioxide concentrations have increased. So the pre-industrial values were something like 280 parts per million by volume. Now presently it is around 417 parts per million by volume. This is a well-mixed gas. It's a long-lived greenhouse gas. And so it has consequences on the climate. But the most important 2 papers came out in the 60s, one by Manabe and Strickler in 1964, where they studied the thermal equilibrium of an atmosphere with convective adjustment. So they proposed they introduced the problem of convection. Once you have the convection is going to basically take the heat and moisture up from the surface to the upper layers of the atmosphere. So basically convection tries to stabilize the whole atmosphere. If it was only a kind of radiative cooling, the atmosphere, if it cools radiatively, the atmosphere is destabilized. And so due to convection takes heat and moisture and the momentum upward, and bring stability. And Manabe introduced the concept of convective moist and dry convective adjustment. This was a very important step. How to represent vertical convection in the models. And he developed the first radiative and convective model. It was not just radiation, radiative convective model to compute the thermal equilibrium. He also computed pure radiative equilibrium. So I will briefly describe this study by Manabe and Strickler. But the landmark paper subsequently, Manabe and Weatherald, 1967, they computed the thermal equilibrium of atmosphere with a given distribution of relative humidity. They fixed the relative humidity of the atmosphere. And that was a very, very important decision they made. And they also, I will come to that in my slides, subsequent slides. And they also had 2 experiments where they doubled the existing carbon dioxide content in the atmosphere. And they found that it had the effect of increasing the surface temperature by about 2.3 degrees. Please keep this in mind, 2.3 degrees if you double the carbon dioxide. And with realistic distribution of relative humidity, which was fixed. And but if you had used absolute humidity instead of relative humidity, the temperature change would be only 1.3 degrees, which is what was they noted. And what they mainly proposed, this was the first very clear demonstration of the water vapor feedback, because once the moisture is getting taken upward by convection, water vapor itself is an important greenhouse gas. It is further going to trap the long wave radiation and amplify the warming. So this this is an important, very nice article from Piers Foster from the University of Leeds. I recently saw that, so I thought I will present this. This picture shows Sukuro Manabe when he was very young with his colleague Joseph Smegoransky in 1962. So the Manabe Weatherald, this is the most influential climate science paper of all time. That's what he says. Where the thermal equilibrium of the atmosphere with a given distribution of relative humidity was computed. Basically, what Manabe did was he modeled the links between temperature, altitude, how the temperature varies with altitude and for different CO2 levels. And what he noted was carbon dioxide heats the atmosphere, increased levels of CO2 in the atmosphere lead to higher temperatures in the lower atmosphere, that is basically the troposphere, while the upper atmosphere, where he is referring to the stratosphere, gets colder. So Manabe just confirmed that variation in the temperature is due to increased levels of CO2. And he also did experiments by changing the solar radiation. In this case, what you will find is the entire atmosphere would warm up. It's not just in the troposphere, but entire both the troposphere and the stratosphere would warm up if it was just increased due to increased solar radiation. Here clearly this picture shows that if you double the carbon dioxide, the temperature increased by 2.36 degrees. Actually, here it is zoomed. This picture has been zoomed. So the red line shows that if you go from 300 parts per million of CO2 to 600, the temperature would increase by 2.36 degrees. Whereas if you make it half of it, if the concentration was brought down to 150 parts per million, the surface temperatures would decrease. And and you can see that the warming is happening at the surface, increase of the surface temperature due to doubling of CO2, you can see, as well as the warming of the troposphere. Whereas when you see in the stratosphere basically the temperature increases with height, but with the doubling of the CO2, the increase with height is at a lower, is smaller as you compare with the control experiment. And this is just a small write-up. So after the Second World War, many of the Japanese smartest scientists found jobs in North American laboratories. Suki Manabe, a 27-year-old physicist, was part of this brain drain. He was working on weather forecasting but left Japan in 1958 to join a new research project by the US Weather Service to develop a numerical model that could be used to study the climate. Working alongside Joseph Smegoransky, the GFDL's visionary first director, Joseph Smegoransky was the first visionary director. Manabe led a team of computer programmers to add missing physics to the Lapse weather model. So they wanted to make a weather model into a climate model. They wanted to add the missing physics. So we should realize that even the best computers in the world at that time were far less powerful than today's mobile phones. So to get the model to work, Manabe needed to make the physics as simple as possible. So he was emphasizing you should make the physics, keep it very, very simple. This meant making a range of coding approximations to quantify how the air exchanged heat and water vapor with the land, ocean and ice. In trying to simplify the code, Manabe and his colleague Richard Weatherall wanted to know the minimum number of discrete levels to use in the model atmosphere. They also wanted to know which greenhouse gases it was necessary to include in the model to adequately represent the way temperatures vary with altitude, as these gases absorb heat emitted by the Earth's surface, but at different levels. But by then they already had a three-dimensional climate model also. Their three-dimensional climate model was too computer intensive to run these model tests, so they had to build a simpler one-dimensional model. So they wanted to simulate how radiation and clouds interact to redistribute heat and water vapor through the atmosphere. So basically the Manabe-Weatherall model is a one-dimensional model, radiative convective model. And the bulk of this paper itself, the focus really was not to look at the effect of increased carbon dioxide. The main idea was to build this model was doing some of the tests, but they wanted to do several tests. But in addition, they did two other experiments to quantify how greenhouse gases might alter climate. And this is where the breakthrough occurred. They found that they had built the perfect model to accurately estimate how human activities could alter the Earth's surface temperature. So their first climate change experiment was not to look at the role of carbon dioxide, but was to look at the effects of water vapor injected into the stratosphere from a potential fleet of supersonic jets. Basically, they're referring to the convection as well as the possible nuclear winter, which were the immediate concerns of that time. However, the table 5 goes down in history as the first robust estimate of how much the world would warm if carbon dioxide concentrations doubled. Manabe and Weatherall estimated 2.36 degrees of warming, not far from today's best estimate of 3 degrees. I will be coming to this. This number 2.36 is a very, very important number. And this is the paper the Manabe-Weatherall paper, thermal equilibrium of the atmosphere with a given distribution of relative humidity. What they did was they fixed the relative humidity distribution in the vertical. And this was a very, very important approximation they did. And so this says that radiative convective equilibrium of the atmosphere with a given distribution of relative humidity is computed as an asymptotic state of the initial value problem. What they found was it takes twice as long to reach the state of radiative convective equilibrium for the atmosphere for a given distribution of relative humidity than for an atmosphere with given distribution of absolute humidity. That means if you have an atmosphere with fixed relative humidity, it will take twice as long. It will be much slower as compared to that with the relative absolute humidity. But the sensitivity, the surface temperature response sensitivity is twice. For example, with fixed relative humidity, it is twice as much as compared to the fixed absolute humidity. And they also try to examine the other role of other factors such as solar constant, carbon dioxide content, ozone, cloudiness, and so on the surface temperature. And they say that according to our estimate, a doubling of carbon dioxide in the atmosphere has the effect of raising the temperature of the atmosphere whose relative humidity is fixed by about 2 degrees. And earlier there was a study by Moeller who was telling that who had suggested that if you had fixed relative humidity, there would be extreme sensitivity of the atmosphere temperature. But his work was based on relative humidity at the surface, and they did not really have a vertical distribution of the relative humidity. And the argument they used, Manabe and Weatherall have used for this fixed relative humidities, even when you go from summer to winter, basically the distribution of humidity, relative humidity doesn't change. And this is the justification they say for making use of this approximation, and which is not a bad approximation at all. And basically the idea of going with fixed relative humidity is that relative humidity being the ratio of the evaporation by saturation, evaporative pressure by vapor pressure by saturation vapor pressure. It depends only on the temperature. That is the important point. But absolute humidity, it is more like density. It is mass of water vapor per unit volume. So it depends on the volume of air. Relative humidity, on the other hand, depends on the temperature. So they identified this very important property. And what they did was, in this one-dimensional model, it's a very simple moist convective adjustment. As I said, they have a simple convective adjustment. They have a dry and moist convective adjustment. So they compute the temperatures at different levels, which are shown by I. And they have a 9-level model and an 18-level model. So they do an integration with time. So this is at time tau plus 1. So they have the value of at the previous time plus the computation of temperature change due to radiation, how much. And they keep on iterating this model, and they do a convective adjustment. So the moment you do a convective adjustment, your profile of water vapor and temperature is going to change. So you compute the mixing ratio of the water vapor. Of course, relative humidity is fixed. You compute the mixing ratio, and once you compute the change in the mixing ratio, you have to compute the mean emissivity and mean absorptivity. And once they do this, then again you compute the temperature change due to radiation. And this whole cycle, the flow chart of the numerical integration goes on. And they used a time step of about 8 hours. And they used the annual vertical distribution of relative humidity with height. This was based on a paper by Telegadas and London in 1954, where they had given this, where they had computed the summer and winter time distributions of relative humidity. And they had also used different clouds, high cloud, low cloud, middle cloud, and what changes in the cloud amount and the albedo. And very cleverly they used, in addition to the convective adjustment, for the radiation absorption of the long wave radiation, they used only 4 bands. And one was a rotation band and a 6.3 micron band of water vapor absorption, and a 15 micron of carbon dioxide, and a 9.6 micron band of ozone. And this was actually done in the Manabe-Strickler paper. They also had the effect of overlapping band between the 15 micron of CO2 and a part of the rotation band of water vapor was incorporated. And if you see, this is you can see this is the incoming solar radiation, maximum radiation intensity in the visible. The outgoing long wave, you can see maximum in the thermal infrared. You have the absorption due to the ozone. This is the 9.6 micron, which they cleverly used. And they also have this for the carbon dioxide, the 15 micron, as well as the water vapor. One is the 6.3 micron as well as the 15 micron band, which overlaps with the carbon dioxide. Just these 4 radiation bands. And I heard another talk by Bjorn Stevens. He gave this problem to one of his students who computed with thousands of bands, and they estimated, did the same calculation. They repeated the calculation what Manabe and Weatherall did in 1967, and they came out with the very same result. So this very clever way of finding the most important radiation bands, because the computing power was very limited, was a very important strategy. This was in, mind you, it was in 1967. And so this is a picture. Basically, the idea was you have how they chose this 4 bands was a very important thing we have to keep in mind. The thermal infrared, which is from the 4 micron to the 50 micron. This is where all the action is there, both in terms of the magnitude of the energy exchanges and also the complexity of the absorption spectra in the atmosphere. And but if you look at most of the typical temperatures in the atmosphere, the 4 radiation bands, they arrived at the conclusion these 4 radiation absorption is good enough to handle, is a first order approximation that you can go with. And this was a very strategic, very practical way of dealing with the problem. And the Manabe and Strickler paper, this came in 1964, where they looked at the thermal equilibrium of the atmosphere with convective adjustment. This is also was an important paper because they examined what would happen if you have a pure radiative equilibrium, and how the atmosphere will adjust if you have a thermal equilibrium, that is radiative and convective adjustment. And so for the pure radiative equilibrium, they performed, in order to prepare the study for thermal equilibrium with convective adjustment, calculations were performed first for the simple case of pure radiative equilibrium, in which the pure radiative equilibrium was approached as an asymptotic steady state of the initial value problem. Whereas in the thermal equilibrium with convective adjustment, the procedure of convective adjustment is to adjust the lapse rate to the critical lapse rate. So whenever you exceed the critical lapse rate, you bring it to the critical lapse rate. For example, they brought it to the pseudo-adiabatic lapse rate of 6.5 degree per kilometer whenever the tropospheric lapse rate exceeded this value. And this is basically important for stabilizing the effect of upward heat transport in moist and dry convection on both short and large time scales. So this is the first thing they identified. Whereas when you take a pure radiative transfer, radiative equilibrium, it has only the destabilizing effect as the atmosphere cools radiatively with height. And so the convection basically tries to stabilize the atmosphere. This is what they proposed. And this is an example again from the Manabe Strickler paper. What they do is they have a radiative convective model where they start the model from a cold state, an isothermal state. This is a cold isothermal state, 160 degree Kelvin, and here you have a warm isothermal state of 360 degree 360, and then it has 18 vertical levels and it has a 8-hour time step. You keep doing this convective adjustment and try to find after how much time the atmosphere reaches equilibrium. And you can see this is the profile of the temperature. You can see the temperature profile initially decreases with height in the troposphere, then decreases with height, and this is after 10 days. And this is the state of the profile after 20 days, 40 days and 80 days. And typically after about 320 days, the profile attains a thermal equilibrium due to radiative convective equilibrium. So you repeat the same analysis both from a cold state and a warm state. You end up with the same type of thermal equilibrium. So that is the idea. And so they estimated that typically it would take about 1 to 2 years to approach this equilibrium from an isothermal atmosphere, whether you start from 360K or 170K. So this was the main idea. So they examined both the radiative as well as the thermal equilibrium. And the main conclusion was the atmosphere in a pure radiative equilibrium and thermal equilibrium. The difference is that the tropopause height in the first case, if it was a radiative equilibrium, the tropopause height would be 10 kilometers. If you have a thermal equilibrium, that is a radiative convective type of equilibrium, the tropopause would be higher. It would be 13 kilometers because of the convection. And when you look at the surface temperature itself at the Earth's surface, if in a pure radiative equilibrium, it would be much warmer. This is typically like the subtropical desert areas. It would be 332.3 degree, they estimated, Kelvin. And whereas in a convective atmosphere, the surface temperature was much cooler because of the clouds, and the convection was around 300 degrees. So and for the atmosphere in radiative equilibrium, they further noted that long wave emission from the ground, because it's a typical, as I said, a desert type of subtropical environment, the long wave emission from the ground to the space plays an important role. Whereas for a thermal equilibrium, the long wave emission from the atmosphere to space is very important, which must be substantially compensated by convective heat transport from the ground. So vertical convection becomes very important when you are looking at the thermal equilibrium. This was from Manabe Strickler. So basically what Manabe and Weatherald in 1967 did was they asked some very basic questions. How long does it take to reach the state of thermal equilibrium when the atmosphere maintains a realistic distribution of relative humidity that is invariant with time, that is fixed relative humidity? What is the influence of various factors such as solar constant, cloudiness, surface albedo, distribution of various atmospheric absorbers on the equilibrium temperature of the atmosphere with a realistic distribution of relative humidity, and what is the equilibrium temperature of the Earth's surface corresponding to realistic values of these factors. And in the simple radiative convective model, they said that the model, it should satisfy these following requirements. One is, they said that at the top of the atmosphere, the net incoming solar radiation should be equal to the net outgoing long wave radiation. Very, very important for climate models. This is the fundamental thing. There should be a radiation balance. This I will be coming at the end. And Professor Manabe, I interacted with some of his colleagues at GFDL. He would always insist that ensuring the radiation balance is very, very fundamentally important. And free and forced convection and mixing by the large scale eddies prevent the lapse rate from exceeding the critical lapse rate equal to 6.5 degree per kilometer. And this is basically the convective adjustment. Whenever the lapse rate is subcritical, the condition for local equilibrium is satisfied. And the atmosphere maintains the given vertical distribution of relative humidity, new requirement. And they also had a ozone, as I said, vertical distribution of ozone, which has an absorption of incoming solar radiation in the stratosphere, which maintains the warm stratosphere. And you can see this is the experiment where they changed the carbon dioxide content. They had 3 experiments. One is a control experiment with 330 parts per million, and one is a doubling of the CO2 600 parts, and one they made it half, that is 150 parts per million. And with the fixed relative humidity, and with the average cloudiness, they did both for average cloudiness and clear cloudiness. You can see an increase when you double the carbon dioxide from 300 to 600. The temperature increase was about from 292.3. The temperature increased from 288.39 to 290.75. This is about 2.36 degrees. And whereas the increase in the temperature with fixed absolute humidity was lesser, much lesser. And this is the vertical profile of the temperature in the atmosphere. So if you had only a radiative equilibrium with fixed relative humidity, the temperature would decrease very quickly, and the tropopause height would be much shallower. And then the temperature increases with height very gradually in the stratosphere. Now, if you do a radiative convective equilibrium with fixed relative humidity, you can see it takes a longer time to reach the equilibrium. But then the height of the tropopause, you have a very deep tropopause. Temperature decreases with height in the troposphere, and the rate of increase of temperature in the stratosphere is smaller with height. And whereas if you had a fixed absolute humidity and radiative equilibrium, again the temperature decrease in the troposphere is happening at a much faster rate and with the shorter tropopause height. And so this is the effect of this is the famous figure once you double the carbon dioxide from 300 to 600, the surface temperature increases by about 2.3 degrees. Whereas it is important to note that in the stratosphere, the increase of temperature with height is less when you compare to the control experiment, that is with the 300 parts per million. So that is the difference. And they also tried experiments where they changed the solar constant by a small number and saw how the temperature profile would adjust. In this case, both the troposphere and the stratosphere would warm. And but in the case of the carbon dioxide, because due to the long wave absorption, the warming you see at the surface and the troposphere, but the warming in the stratosphere is reduced compared to the control experiment. And the most important thing is the increase in the surface temperature with fixed relative humidity. When you double it, under average cloudiness, the temperature increase is plus 2.36. That number is very important. We'll come to that again. And these were the conclusions. Generally speaking, the sensitivity of the surface equilibrium temperature upon the change of various factors such as solar constant, cloudiness, surface albedo, and CO2 content are almost twice as much for the atmosphere with a given distribution of relative humidity as for that with a given distribution of absolute humidity. So this was in 1967, and I heard from some very big scientists that people tried to understand why they use this relative humidity, fixed relative humidity. They spent 40 years. Even after that, they came to the same conclusion. So to understand why he did, it took them a very long time, and the speed of approach towards the state of equilibrium is half as much as the atmosphere with a given distribution of relative humidity as for that with a given distribution of absolute humidity. So the speed is much slower if you use the fixed relative humidity. It takes twice as long. In other words, the time required for radiation condensation relaxation is much longer than that required for radiation relaxation of the mean atmospheric temperature. And doubling of the existing CO2 content of the atmosphere has the effect of increasing the temperature, surface temperature by 2.3 degrees for the atmosphere with realistic distribution of relative humidity, and about 1.3 degrees with realistic distribution of absolute humidity. And so these are the main findings. I will now go to the main paper. And Manabe also pioneered many other experiments. Beyond this, he also went on to developing more sophisticated versions of the climate models. In 1969, he had developed a model including the ocean circulation. And they looked at not only the atmospheric circulation, also the hydrology of the Earth's surface. And so this is the effect of hydrology on the Earth's surface is incorporated in a numerical model of the general circulation of the atmosphere developed at GFDL. And by this time, they had developed a model for the soil moisture, what is known as the bucket model. And so they said that the amount of moisture the soil can hold, they had defined what is known as a field capacity. Once it exceeds the field capacity, the remaining water from the soil is allowed as runoff. And through this very simple model, they were able to compute the qualitative features of hydrological and thermodynamic regimes at the Earth's surface. They could successfully calculate. This was 1969, mind you, and they could get the distribution of rainfall and evaporation, which was an excellent qualitative agreement with observations. They could simulate the typical subtropical deserts, the break of the subtropical dry belt along the east coast of the continent. And basically this model, they were focusing on the region in the Atlantic. This is basically in the Atlantic region where you have the Atlantic Ocean. This is the sea area, and to the west you have the North and South America, the continents. So it is domain is limited, but it extends from North Pole to the South Pole. And in the east-west direction, they used cyclical boundary conditions. Very cleverly, so they took the region of the Atlantic Ocean and the continent, the American North and South American continents. And this was the first atmospheric general circulation model where they could simulate the general hydrological process, the subtropical deserts and the heavy precipitation areas in the tropics they could compute. And later on, with Kirk Bryan, around the same time, he had developed an ocean model for the Atlantic. So this is the first coupled model, Manabe and Kirk Bryan, climate calculations with a combined joint ocean atmosphere model. Because by that time there were some observations that were indicating the poleward transport of heat by the ocean currents is of the same order of magnitude as the poleward transport of energy in the atmosphere. This was by Sweldrup in 1957. And they immediately recognized that it's important to couple the atmosphere and the ocean. A significant contribution to the heat exchange across latitude circles is also associated with polar ice pack, because this has implications. Once you have an ocean and atmosphere coupling, it has implications on the sea ice in the North Atlantic. Thus, any serious attempt to compute climate must take into account the entire fluid envelope of the Earth, consisting of the atmosphere and the hydrosphere. Although the cryosphere, consisting of ice packs over the oceans and continental ice, is not a fluid in the usual sense, it must be included in the general circulation model because of its large reflectivity of the solar to the solar insolation and its ability to store and transport heat. And so these two models, the atmosphere and ocean model, atmosphere model by Manabe and Kirk-Bryan's ocean model was coupled, and they produced the first combined climate simulation for the Atlantic Ocean. You can see this is the computed temperature in the atmosphere, and this is the observed temperature vertical distribution. And in the ocean, they are able to simulate this subsurface temperature distribution. Pretty much considering that this was nearly more than 50 years back, 51, 52 years ago. And the most interesting result of this calculation is the quantitative demonstration of the effect of ocean currents on the distribution of temperature, relative humidity, and precipitation patterns. So this is one, and they also, and subsequently, the effect of the carbon dioxide doubling on the using the one-dimensional model, the Manabe weather, they reproduced it. They also examined with a full climate model, general circulation model, and this was in 1975. They showed that the important point is the doubling of CO2 significantly increases the intensity of the hydrological cycle. And this was 1975. They have proposing that the hydrological, if you double the carbon dioxide with increasing climate change, hydrological cycle is going to get intensified. And this is the assessment we are also telling now in the latest assessment report. So so that means basically the tropical, the equatorial areas where the precipitation dominates is going to get stronger, and areas in the subtropics where dry areas where descent, they are going to get drier. So it's like the rich gets richer and the poor gets poorer. So wet gets wetter and dry gets drier kind of paradigm. That's what we expect with climate change. And interestingly, they also examined, Manabe had also worked with Hahn. This is the famous paper, Hahn and Manabe, on the role of mountains on the South Asian monsoon. This was in 1975. They cleverly, they could remove the effect. If I take out the Tibetan Plateau and the Himalayas, what happens to the monsoons? And of course, those days, the resolutions of the model was coarse, we have to keep in mind. So with and without the mountains, what will happen to the South Asian monsoon? And they said the comparison of the simulations with mountains and the simulation without mountains reveals that the presence of mountains is instrumental in maintaining the South Asian low pressure system, as the continental low forms far to the north and east in the simulation without mountain topography. And they also say the precipitation extends much into the land region when you have the mountains, whereas in the no mountain experiment, the precipitation is mostly to the south, much to the south in the Asian continent. So they suggested that mountains are very, very important, especially the Tibetan Plateau and the Himalayas for the monsoon, South Asian monsoon. And this was another paper by Broccoli and Manabe on the effects of orography and mid-latitude dry climate. And he used to tell me this paper they wrote keeping the geography people in mind. Why the dry climates are happening. This was the basic idea of the paper. Usually much of the dry climates are in the subtropics, like the Sahel region or the subtropics in Australia and South America, North America. You can see them, they are all in the Sahara region, even the Thar Desert, they are all in the subtropics. But there are some areas where the dry arid regions are in the mid latitudes, like the Gobi Desert over Asia, or also you have some over the continental US, some areas of dryness in the mid latitude continental areas. So they wanted to say what is why these mid latitude deserts happen over the continents, and what is the effect of orography. And so they did experiments without, and so what is the effect of these big orographic barriers like the Tibetan Plateau and the Rocky Mountains. This is basically the classification of arid and semi-arid climates based on the Köppen classification. These are the arid and semi-arid areas you can see, and they did 2 experiments with and without mountains. Okay, and what they found was if you remove the mountains, much of the aridity that you see over the Gobi region would disappear. So in the present day, what you see, the Gobi Desert, he says it is basically happening because of the summertime, the influence of he says the dryness of the interior Eurasia in summer results in part from the South Asian monsoon circulation induced by the Tibetan Plateau. Its rising branch is centered above the southeastern Tibetan Plateau and an anticyclonic flow in the upper troposphere. This circulation is associated with northward displacement of the storm track and a flow of relatively dry subsiding air across much of South Asia. So if you remove the Tibetan Plateau, interestingly, the aridity in the Gobi Desert region it decreases, and they further argue that the results from this experiment suggest that mid-latitude dryness is largely due to the existence of orography. This is an alternative to the traditional explanation that distance from the oceanic moisture sources accentuated locally by the presence of mountain barriers. Upwind is the major cause of the mid-latitude dry regions. And they further argue that paleoclimatic evidence of less aridity during the late tertiary before substantial uplift of the Rocky Mountains and Tibetan Plateau is believed to have occurred supports this possibility. So they were also looking at paleoclimatic implications of this. And this was a more recent paper in 2004, again Manabe, Weatherald and Millie, Delworth and Stauffer on century scale change in water availability due to quadrupling of CO2. So they have really examined that even at the river basin scale, this was with a full coupled model. It has been suggested that unless a major effort is made, atmospheric concentration of carbon dioxide may rise above 4 times the pre-industrial in a few centuries. That's what they have proposed. So if this happens, if you quadruple, and it's a very huge increase in the carbon dioxide, what will happen to the water availability? They find that many of the rivers and in the semi-arid regions, they are going to go dry, especially in the Mediterranean region, southwestern region of North America, northeastern region of China, and so on. Whereas they also looked at some of the tropical areas. In the tropics, discharges from the Amazonas, the Ganga and the Brahmaputra river basin, they will increase substantially. So they are looking at the hydrological response, what will happen to the hydrological cycle at the river basin scale. And this was another paper where with Manabe and Delworth, a very interesting paper on how soil wetness can impact climate. So basically they argued that if you look at the temporal variability of soil wetness and its interaction with the atmosphere, they studied with a general circulation model. They found that if you take the time series of soil wetness computed by the model, they found significant low frequency variability, the soil moisture. But if you look at the time series of precipitation, it is more like a white noise spectrum. So the question is how this white noise can transform into a low frequency red noise of the soil moisture time series. So basically they argued that the long time series timescale anomalies of the soil moisture resemble the red noise response of the soil layer to white noise rainfall forcing. And the dependence of the temporal variability of soil moisture and potential evaporation and precipitation discussed. This is a very, very important paper where this is based on they use the bucket model, which is basically a first order Markov process. And this work, they refer to the Hasselmann paper of stochastic theory of Hasselmann, which Hasselmann applied in 1976 to understand the ocean and atmosphere interaction. And he argued that ocean acts as a long-term integrator of white noise, thermal forcing from the atmosphere, thus supplying a long memory, that is red noise component to the atmosphere-ocean system. A similar white process may exist over land, whereby the soil acts as an integrator of white noise, atmospheric forcing precipitation, thus supplying a long memory, red noise component to the atmosphere land surface system. So this was a very important paper, how the soil moisture memory comes, because it acts to integrate the white noise. So, and this we have also used in some of our assessments of our soil moisture measurements here. And later in the late 70s and the 80s, Manabe and Brand, they pioneered the fully coupled climate models. where they developed a mechanism of exchanging the evaporation sensible heat from the ocean to the atmosphere, and whereas from the atmosphere they provide the precipitation as an input and the radiative transfer and the surface stress as input to the ocean. So they coupled the ocean and the atmosphere, and so several studies came out of this to understand the climate. This is taken from Manabe and Stauffer. And later, Manabe, Stauffer, Spellman, and Brand, they also studied the impact of the freshwater this is the transient response of a coupled ocean atmosphere to gradual changes in the atmospheric CO2. So if you, they did 3 long experiments. This is with a fully coupled model. You have a control experiment for 100 years with the present day carbon dioxide. And they had 2 experiments, the G integration, where carbon dioxide is increased at 1% per year, compounded at a rate of 1% per year. So it takes typically at 1% per year, you double it in 70 years. The concentration becomes double in 70 years. And in another experiment, it is decreased by 1%. So it becomes half of at about 70 years later. So they compare the 3 experiments. They're basically focusing on the effect of this on the climate. One thing they documented was that if you make changes in the carbon dioxide in these transient experiments, it is noted that the simulated response of sea surface temperature is very slow over the North Atlantic and the circumpolar ocean and southern hemisphere, because in these areas, especially in the North Atlantic, the density is very high because the waters are very cold and very salty. It's very high density, and it's a thermohaline circulation because it's driven by the density gradient. It's also now known in the literature as the Atlantic meridional overturning circulation. Deep oceanic circulations in the Atlantic Ocean due to sinking of dense waters in the North Atlantic, and they noted that in the simulated response, the surface temperature is very slow over the North Atlantic and the circumpolar ocean of the southern hemisphere, where vertical mixing of water penetrates very deeply. That's an important point. And when they change the carbon dioxide concentration, what they noted was as the polar regions, as they get warmer and the ice melts, you are introducing more heat in the polar region. Also, you are freshening the North Atlantic. So once you freshen it and also add heat, the density is going to decrease. So the density gradient can weaken and the thermohaline circulation basically weakens. So changes in the polar ice. So if you see, this is the control experiment. You have in the high latitudes, the sinking of the cold water, and this is the deep meridional overturning circulation. So once you increase the carbon dioxide, the stream function, this is known as the meridional stream from overturning circulation, the circulation weakens. And further, when you decrease the carbon dioxide at 1% per level, and when it becomes half of the initial concentration, you can see that the oceanic circulation intensifies. And they found that you can see that when you decrease the carbon dioxide content, the time-dependent response of the global mean surface temperature in the CO2 reduction experiment is similar in magnitude to the corresponding response of CO2 growth experiment. In the former experiment with colder climate, as you decrease the CO2, you produce colder climate, snow and ice pack with higher surface albedo. They cover a much larger area, thereby enhancing the positive feedback effect upon the surface temperature. So you can see that virtually they have gone into, and they also use this approach to study abrupt climate change in paleoclimatic timescales. And also they have more recently, they have also in the last 20 years, they also examined the effect of ENSO, tropical phenomena like El Nino Southern Oscillation, how well they are simulated in the coupled model. And they had examined long simulations, something like 1,000-year simulations. This is Knudsen, Manabe and Gu, where they simulated the ENSO in the coupled model, and they compared with the paleoclimatic data. Some of the coral records in the Galapagos, they provide a proxy for how the ENSO has varied. And so this ENSO variability they studied with the model. And they also studied the effect of climate change, whether increasing carbon dioxide will affect the amplitude modulation of ENSO. So although the ENSO scale is about 3 to 7 years, it can undergo amplitude modulations. That is, used to tell the amplitude modulation is about several decades. Some decades the amplitude of ENSO is very large, and some decades the amplitude is very low. And these amplitude modulations are several decades, and that they could see in the model simulation, also in the coral records. And they studied the effect of CO2 increase on the amplitude modulation of ENSO, and they suggest that the results suggest that the impact of increased CO2 on ENSO is unlikely to be clearly distinguishable from the climate system noise in the near future, unless ENSO is substantially more sensitive to increased CO2 than indicated in the present study. And this was another paper which is very important. They looked at the Pacific decadal variability. There is like the ENSO, there is also something known as a Pacific decadal oscillation, which the patterns of sea surface temperature, the pattern of heat content evolution, they all look very similar, but only that it evolves slowly. The heat content evolves very slowly on decadal time scale compared to the intraannual, the ENSO time scale. And he studied what is the, and for example, when you look at the SST trend, this is the observed linear trend in the sea surface temperature. You get, this is from the period 1949 to 1994. You get this warming pattern in the central and eastern Pacific, a triangular like pattern, and cooling in the north and the North Pacific and the South Pacific. Okay, this is a typical pattern of the PDO, Pacific Decadal Oscillation, where you have this triangular warming in the central and eastern Pacific and cooling in the North and South Pacific regions. And when you look at the time series of this pattern itself, it has this interdecadal variations with a trend, with a kind of increasing trend from the 50s. So they wanted to understand whether climate change, whether increasing concentration of carbon dioxide has an implication on this increasing trend of the PDO. And so they did this coupled model experiments with increasing carbon dioxide from the pre-industrial and with the control experiment. They had two simulations of the 20th century climate change, and the results simulate an accelerated warming trend in the triangular Pacific pattern beginning around 1960s, and suggest that nearly all of the recent warming in the region could be attributed to such a thermal forcing. And yeah, so in summary, the author model results indicate that the observed warming trend in the Eastern Pacific is not likely to be solely attributable to internal natural climate variability. Instead, it is likely that a sustained thermal forcing, such as increasing greenhouse gases in the atmosphere, has been at least partially responsible for the observed warming. So they're arguing that the Pacific decadal warming is also the warming trend that you see in the PDO could be because of the influence of greenhouse gases. And so these are some of his brilliant contributions. Professor Manabe also provided strong collaborative scientists to climate scientists from India. And the first being, I would like to draw attention to my PhD guide supervisor, Professor R.N. Keshavamurthy from PRL. This was in 1987. I joined PRL as a PhD student, and it was a small group, and Professor Keshavamurthy had worked with Professor Manabe in GFDL. Earlier, people had known that in 1987, there was one of the big droughts in India. Monsoon was very deficient. It was also an El Nino year. And previously, 1982-83 was also a big El Nino, one of the biggest El Ninos we have seen. And monsoon was also deficient in 1982. But the deficiency was much more in 87. I remember that in Ahmedabad, when I went, it was very, very dry during that time. And this famous work by Professor Keshavamurthy, he had worked with Professor Manabe and in GFDL, and he had done these experiments by introducing sea surface temperature anomalies in the GFDL model in the Eastern Pacific, Central Pacific, and Western Pacific. And they found that when once you put these were idealized sea surface temperature anomalies, the anomaly that in the Central Pacific has the most strongest influence on the monsoon. And earlier, if you had seen earlier, people were aware of the ENSO monsoon teleconnections, starting from the works of Walker and Bliss, Norman, Trube, and others, and Professor Sikka from IITM, Pant and Parthasarthi. They had documented the link between the southern oscillation and monsoon rainfall, and later Rasmussen and Carpenter. So observationally, it was all very well documented even before. But Professor Keshavamurthy's first work on this, using a general circulation model with this collaboration with Professor Manabe, was a very, very important contribution in demonstrating through a general circulation model how the El Nino can affect the monsoon. And so at that time I had joined, and there was a small group. Professor Keshavamurthy, Dr. Satyan was there, and my senior V. Krishnakumar, who taught me many things about monsoon because I was just a novice. So many things I learned from him, and Kastureji, who was our very competent climate. He was the person who did all the programming and did all the computational work. And those were the time when the modeling work really started, that time. And I want to acknowledge that. And subsequently, because in the first paper, 1982, this work was based on idealized anomaly. The subsequent work in 1983, he repeated with observed anomaly. By that time, the NOAA satellites were measuring the sea surface temperature as well as the OLR, long wave radiation. So we had the information about sea surface temperature and convection over the oceanic areas by this time. And this was from Rasmussen Carpenter. They had this observed temperature SST anomalies. This was from Keshavamurthy, had used this for the summertime anomaly and examined how in the GFDL model the circulation patterns and the precipitation, how the southern oscillation responded. Later on, even Krishna Kumar has subsequently, many years later, Krishna Kumar from IITM also showed the influence of the Central Pacific on the monsoon, and also Ashok. So these are all many important contributions that I've documented. And many years later, Professor Goswami, who was in IISc, he also visited GFDL, worked with Professor Manabe, and he looked at the intraannual variation of the monsoon. In this case, he was looking at the internal feedbacks. What is the role of the external conditions versus the internal feedbacks? When I say the external, basically the ones like what Professor Keshavamurthy was talking about, the effect of external climate drivers like ENSO, these are boundary forcing, how it affects the monsoon. But what Goswami was looking at was at the internal feedbacks, whether there are non-ENSO mechanisms, whether there are internal mechanisms that affect the monsoon. And they did document the importance of the internal variability on the monsoon. This was in 1998. And so this was all the beginning, and subsequently Professor Keshavamurthy, he started the climate and global modeling division in IITM. That was an important because of the appreciation of the role of climate models. If you want to really advance climate studies, models are going to be important. And the climate and global modeling group was started, and it was later strengthened. And by the time during Professor Goswami's tenure, the CCCR, the Center for Climate Change Center, was also initiated by the Ministry of Earth Sciences in 2009-10. And so these are all some important developments. And now I would like to present some reminiscences of interactions with Professor Manabe when I had visited the Frontier Research System for Global Change during 1998 to 2000 as a visiting researcher. And this was my 2 years, and this was the time, and this is with Professor Matsuno. This was during an award ceremony. Professor Matsuno is another big legend in meteorology, made pioneering contributions in the tropical meteorology, in the tropical atmospheric dynamics, sudden stratospheric warming, equatorial dynamics, and even the numerical integration. And so this was during the award ceremony I received, and he was our Director General at the Frontier. And this is Professor Manabe and Professor Matsuno, two giants, two great leaders. And along with me, you can see Dr. Behra, Swadhin Behra, and Saji. And Saji had done a very wonderful paper on the IOD, Indian Ocean Dipole. And this was with Professor Yamagata, again, landmark contribution. And in fact, for that IOD paper, I remember Professor Manabe telling that you should include in your composite, because 1994, 1997, big IOD events, he was suggesting you should go back in time and see whether you have more IOD events. That makes your analysis very robust. So he was a great mentor, Professor Manabe, and used to give great ideas. And this is Dr. Masato Sugi, with whom I did my work. He was the group leader, he was my host, and Professor Manabe was actually the program director. And this was during the farewell ceremony, and I had also took my family to the farewell. And this is in Professor Manabe's office. This is our son, who's very small, 3-4 years at that time. And this is in his office. And Professor Manabe had this childlike curiosity. For him, curiosity-driven research was very, very important. And you can see this big dinosaur hanging. And I still remember telling about these dinosaurs and during ice ages, how and long back, how these reptiles existed and so on. So he was fascinated with science. And later I had an opportunity to visit Princeton. This is with his, he was very kind to take me to his home, and this is with his family. This is his Rossby medal, and this is Professor Mrs. Manabe's with Manabe. So he's a great human being, wonderful person, and a great leader. And regarding my work, one of the works that I did, he gave great ideas, was looking at the monsoon break using OLR. Earlier, many people had studied breaks in the Indian monsoon. For example, during a typical monsoon rainy season, which goes from June through September, many times within the season, there are many days where the rainfall is very low. And this is, for example, 2002, the entire July was very dry over much of the country, and it resulted in one of the big droughts. So if you have this type of long breaks during the season, you can end up in a drought. And people had looked at the data from the rainfall data. This is by Ramurthy in 1969 from the IMD data. They had looked at how much is the rainfall deficiency during monsoon breaks. This could be something like 75–80% over central northwest India, large deficiencies. And incidentally, during this time when the entire country is dry, parts of Tamil Nadu, which usually don't get much rain in the summer monsoon season, they get rain during the breaks. And also over northeast India, over the foothills, Himalayan foothills, you get rainfall. And this is a subsequent work by Dr. Rajivan, our former secretary, and also Professor Slochana Gadgil Joseph. They have also looked at monsoon rainfall breaks using the rainfall data. But at that time when I went, I did not have this gridded rainfall, and I wanted to look at breaks. So we thought of using the OLR, the outgoing long wave radiation. And basically the outgoing long wave radiation, as I mentioned even the early, this is what we call as the OLR at the top of the atmosphere. This is now available from the satellite measurements. And what this OLR indicates is, as I said, when you have a convection, a thermal atmosphere, where you have radiation and convection, you have deep convection, as in the summer monsoon region. You have high clouds, a lot of cloud coverage. So the cloud top temperatures are very low. The long wave OLR is very, very low in that place. It could be much less than 220 watts per meter square. Okay, and it could be as low as 180 watts per meter. These are all areas with very deep convection, lot of cloud cover. And when you go to the dry areas like the desert areas where you don't have cloud, it's all clear sky. So the OLR is very high. It could be more than 290, even more than 300 watts per meter squared. So high OLR means a scarcity of cloud cover. And if you have low OLR, it means it is the regions of deep convection. Now, if you see the satellites in NOAA advanced very high resolution radiometer, it integrates the radiation, infrared radiation. This is the thermal infrared radiation between the 10 micron and the 30 microns. And they are mainly sensitive to the surface temperature and the cloud temperatures. And so we used this data and we said, why not, can we not understand monsoon breaks using OLR? And Professor Manabe was very interested. He got excited because he said, yeah, this is the way to look at convection. What is happening to the convection? And if you're looking using convection to study from OLR to study convection monsoon breaks from the satellite, it's a great idea. And he told the pioneer of remote sensing was Vern Suomi. He pioneered this from the University of Wisconsin-Madison. He pioneered this measurement of the long wave radiation to understand clouds. And then that's how this paper started. This was a famous paper. I shouldn't say that. It's an important paper that came out with Dr. Sugi and Chidong Zhang, where we looked at the OLR data and identified days of high OLR because of lack of cloud cover. And this is a composite. You can see that when the breaks are there, it is not just the break is limited over India. It is a much larger pattern extending all the way into Southeast Asia, into the Philippines and the Indonesian region. And it's a kind of quadrupole pattern. And the OLR anomalies are something like more than 30 watts per meter squared. And individual, some of the extreme cases could be even much larger. And when this is a composite of many, many cases. And usually when the breaks are happening, you get more convection over the Indian Ocean and over this over Taiwan and Japan and this area. This is an important point. And we also want this monsoon circulation. So when the convection break gets suppressed over this very large area, the monsoon circulation becomes very weak, substantially. So in the low level, the southwest monsoon circulation weakens. So you get an anomaly, you get an anticyclonic anomaly. And in the Pacific, you get a kind of what is known as, now in the literature, you get an intensified, a kind of north-south cyclonic pattern to the north and a anticyclonic pattern to the south. This in the literature, we call this as the PJ, Pacific Japan pattern by Nitta. And so we did some modeling, and you can see this convection pattern, this high, the suppressed convection basically develops. This is the time of the break. And when you go back in time, it starts in the Indian Ocean, progresses, it spreads like a Kelvin wave as you go eastward. And when it reaches this suppressed convection, it moves over India suddenly in a matter of few days, and the break commences. That is what is the commencement of the break. And a few days later, we start seeing the development of the increased convection over the equatorial Indian Ocean. And we had also used a simple model. And this paper, we got very important comments from Professor Manabe, not only during writing the paper, he also during the review, he provided very, very important comments. And also Professor Yasunari, to whom we acknowledge this paper. And also this was, I could visit Frontier thanks to support of Professor Pansab, who was our director, Dr. Satyan and Dr. Soman. I could visit, and basically we said we did some simple experiments with a very simple model that I had developed at that time. By putting, if you see this suppressed convection, it is basically a kind of you are radiatively, you are cooling. There is a lack of cloud cover. You are basically cooling the atmosphere. It's a clear sky condition. And so it's a kind of a heat sink. If you have, so we had a model where we apply a diabatic heating, develop a simple idealized monsoon circulation. And we prescribe this radiative cooling, a heat sink. And so we introduce an initial perturbation. So a high pressure anomaly develops. And then we see what happens to the high pressure anomaly. And this high pressure anomaly, it moves westward, mostly due to the effect of the beta effect. And within a few days, you see this break, commencement of the break. This was, and we said this resembles more like a Rossby wave. We also looked at the circulation patterns from the reanalysis data. We suggested that the evolution of the break is due to a kind of a Rossby wave that is generated. It's like a Matsuno gill type of pattern in response to the convective anomalies. And he appreciated this paper very much, also from the dynamics point and also from the point that we use the OLR data to identify the convection. And the other paper was, we also studied the Bayou. As we have the summer monsoon rainfall during June to September, Japan gets rainfall mostly what is known as the Bayou in the early during May, June, and some part of July. And so the overlapping period between the Indian monsoon and the Bayou Japan is June and July. And as I said in my earlier slide, whenever we have a break, we tend to get increased convection in over the Japan region. So I thought, why not whether I wanted to understand if there is a connection between the Bayou and the Indian monsoon. And at that time, I was trying to look at long period data. And for India, fortunately we have a very long record. Thanks to Pant and Parthasarathi, thanks to IMD, we have a very long-term record. In Japan also they have a very long-term record. But when I started collecting, there were some when I looked at the NHC and the historical climate network, there were some break in the data during Second World War. And at that time, Japan was very badly affected. And I spoke to some of my colleagues and they told that why not you go to the Bosaiken library. So I used to work in Tsukuba at the Frontier Research Center for Global Change in Tsukuba, and they had a beautiful library. And there's Suzuki-san, one of the scientists, he told me how to identify he gave me the kanjis, the Japanese characters for the different stations, Tokyo, Kyoto, and all these stations, the kanjis, he wrote them for me. And he told you will get the data if you go and check the records. The JMA records may contain that, you go and why not you dig out. So he pointed me how to do that. And with that I could I could get hold of 16 stations without gaps in the data. And so when we then we reconstructed the Bayou rainfall from 1900 to 1994, and we also had an Indian monsoon rainfall. And this is I've shown over North Central India. This is a kind of pattern. And first I was trying to do this whole thing starting from going from Indian monsoon to the Bayou. I remember Professor Manabe telling me that you should start from Bayou and go to the Indian monsoon. So he would give this type of very practical ideas. So because the common type, what is the connection between the Bayou and the Indian monsoon? So this is a PC EOF of the Bayou rainfall, and this is the first principal component. These are the EOF loadings. You can see much of the Bayou activity is mostly in the southern part of the Kyushu and Shikoku Islands, and also in the southern Honshu. And we see that this is the pattern over India. We see an out of phase variability. So whenever the Bayou is stronger, we get kind of less rainfall over India and vice versa. And this correlation is about 0.4, which is not bad. And given that it is very long term, it's a statistically significant. And when we look at a long term surface temperature data, air temperature and SST merged product, so whenever it is a wet minus dry composite, so when you have a wet minus dry, when you have more precipitation, surface temperature increases over the land areas. And so you can get more cooling. As surface temperature decreases, you get a cooling pattern. And over North Central India, when the rainfall decreases, you get the anomalous warming. And we noted two patterns. One is that PJ pattern, the Pacific Japan pattern by Nitta. And the other one, a kind of a continental pattern, we called as the Asian continental pattern, which actually has a very large scale cyclonic. This is in the middle and the upper troposphere. Basically, the cold air sinking over the northwest India, it produces dry subsidence and weakens the monsoon. And then you can have a kind of anticyclonic anomaly over Mongolia and a cyclonic anomaly in the Far East. We called it as the Asian continental pattern, which explains this connection. And subsequently, there was a paper by Yamamoto and Hoskins. They refer to the same pattern as the Silk Route pattern. So they also agree with this type of interesting teleconnections that came out, and Professor Manabe greatly appreciated and supported this work. And lastly, he also taught me a lot about the Pacific decadal oscillation, which he had done. And he told me many times, you remember Pacific Decadal Oscillation is different from amplitude modulation of ENSO. You be very clear about it. And because we had submitted this paper to GRL, it was rejected due to a lot of comments. He told you need to very clearly tell why PDO is different from ENSO. Unless you do that, it's going to be tough. And he told there is a lot of confusion between the PDO, the amplitude modulation of ENSO, between the North Pacific oscillation. So there's a lot of confusion, and you don't add more confusion to that. So he used to give very important ideas, and when we looked at this PDO and its teleconnection with the monsoon, it is very similar to the ENSO, and so we out of phase variability. And this paper also subsequently, the reviewer, one of the reviewer who actually was not, he gave his comments, Fedorov, he disclosed his identity. He told it's a fantastic paper. He gave very nice comments to add, clarifying the difference between PDO and the amplitude modulation of ENSO. So thanks again to Professor Manabe. And most importantly, his idea of radiation balance, he always enforced, he was telling that having the radiation balance at the top of the atmosphere is very, very important for our climate studies. And this is something which we persistently followed. We had the first version of the IITM Earth System model in 2014. It could capture all the modes of variability, good ENSO, El Nino Southern Oscillation, monsoon was reasonably good. But when we want to go to climate, the radiation balance has to be satisfied. Unfortunately, the first version had an imbalance at the top of the atmosphere, the outgoing radiation and the net radiation balance was, we had an excess of about 7 or 8 watts per meter square. And clearly it was not suitable for climate change studies, for studying the effect of increasing CO2. So when the second version was needed, we focused on how to make a radiatively balanced system. Just focus on getting a radiatively balanced system. So this was by Swapna et al. In the paper in 2017, 18, it came final print. We got a radiation balance. It was not perfect zero. It was close to 0.7 or 0.8 watt per meter squared. We reduced a lot of biases, and this is a 500-year pre-industrial control run with fixed CO2. We got a radiatively balanced system, and the problem was happening was because of the ice, with the Arctic ice, sea ice distribution. In the version 1, we realized that the Arctic sea ice was very much underestimated. And as I said, it was getting more warmer in this region, the temperatures were warm. And also because of the melting of the sea ice, we were adding a lot of fresh water. So due to the addition of the fresh water and heat, and due to the loss of the Arctic ice, the Atlantic meridional overturning circulation was practically absent in the version 1. So we focused our attention to get the radiatively balanced system. We decided to focus on improving the Arctic ice and the Atlantic meridional overturning circulation. This is again something we learned from the GFDL experience and also the experience talking with Professor Manabe. And this is the version V2, where we have a perfectly very nice radiatively balanced system. Improved Arctic ice, also in the Antarctic, also the sea ice is distribution, and we have a very nice AMOC, Atlantic meridional overturning circulation, and we have a near perfect, a good, very nice energy balance, incoming radiation and outgoing radiation. And this is the model. The version 2 was the one we used for our climate projections, and what we find is that this is from our annual MOES climate change report. These are our projections for the different scenarios, the temperature change, precipitation change, and the sea level change. We are doing very much comparable to most of the models. And in fact, among the many CMIP 6 models, they are generally projecting a higher temperature compared to the CMIP 5 models. And the IITM model is shown in the solid line. This is for the SSP 585 and this is for the SSP 245, the blue line. And this is for also the precipitation is projected to increase global mean precipitation in the future. Slightly more in the CMIP 6 compared to the CMIP 5. We have also shown the IITM ESM by the solid lines. And this is the thermospheric sea level changes. And so it's one of the good models. It has a very important contribution again coming from India. and the participation of this model in the IPCC AR6 report. And this is one final point I want to tell. Among the in the CMIP6 and the AR6 projections, we have different scenarios. The SSP 245, I'm particularly drawing, this is the middle of the road scenario, where the carbon dioxide by the end of the 21st century would be close to double of the pre-industrial value, something like 560 parts per million. Now, so this is a kind of a doubling of the scenario compared to the pre-industrial value. And with this, let us see what is the value of the temperatures by the different models and what Professor Manabe had estimated. So in the 245 scenario, for the near term, that is 2021 to 2040, this is from the IPCC AR6. The best estimate in the near term from multiple models, CMIP6 is 1.5. In the midterm, that is 2041 to 60 is 2-degree estimate, and we are also giving the very likely range. And the best estimate, that is 2081 to 2100, is 2.7. And this is at the time of doubling, to just recall. And this is from the IITM ESM. So the interesting point is IITM ESM for the SSP 245, the near-term value is 1.38. IITM ESM has a slightly lower sensitivity compared to the many of the high sensitivity models in the AR6. And the most interesting point is so this should be 28, sorry, this last value is 2081 to 2100, not 2061. So the value is 2.3, almost very close. Manabe's was also 2.36, this is 2.3. So the projection that we are getting is very, very close to what he indicated. That's very interesting. The courtesy Swapna for this slide. So we also, this experience also helped me to be as a participant in the water cycle changes chapter in the AR6. That is one more thing, as a CLA in one of these chapters. And monsoon was a very key point of this water cycle chapter in the AR6 assessment report. And we assess different components of the water cycle. And many of the assessments, research contributions that Professor Manabe had done, we could validate that in with the latest model simulations, the CMIP5 and the CMIP6, and it also came out with very important messages that human-induced climate change is already affecting weather and climate extremes already. This is for the current climate system. It's already affecting in every region of the globe, and we are seeing many extremes such as heat waves, heavy precipitation, droughts, and tropical cyclones. And their attribution to human influence has strengthened since AR5. And of course, we made very detailed assessment of both greenhouse gas forcing as well as aerosol forcing on the monsoons. I'm not going into the details. And with reference to the water cycle, particularly, we said for the future, with continued global warming, the water cycle is projected to intensify. Not just the water cycle, also its variability is going to intensify, and the global monsoon precipitation is going to intensify, and the severity of the wet and dry events is projected. All that something Professor Manabe and his team had long back with Weatherald and team they had shown, and these are emerging very clearly nowadays. And the point is a warmer climate will intensify very wet and very dry weather and climate events and seasons with implications for flooding and drought with high confidence. But the location and flooding of these events depend on projected changes in regional atmospheric circulation, including monsoons and mid-latitude storm tracks. Monsoon precipitation is projected to increase in the mid to long term at global scale, particularly over South and Southeast Asia and East Asia and West Africa, apart from the far West Sahel. Medium confidence. And so the AR6 has come out with very strong, so climate change is happening, extremes are already happening. Right now, Chennai is experiencing a lot of heavy rains, and it has been very persistently lasting for several days. And the low pressure has intensified into a depression, and these type of events are becoming more and more frequent. And the IPCC report came out with very strong statement. It is unequivocal that human influence has warmed the atmosphere, ocean, and land, and the changes are widespread and rapid in the atmosphere, ocean, cryosphere, and biosphere. And climate change is affecting every region on Earth in multiple ways. The changes we experience will increase with further warming, and unless there are rapid and large-scale reductions in the greenhouse gas emissions, limiting warming to 1.5 degree will be beyond reach. So these are important points. So with although the extremes are increasing and we have made great progress, significant progress in short-term weather predictions and improving our early warning systems, improved our predictions of tropical cyclones, especially from the MOES, from the IMD, from IITM. So compared to the last 20 years, the predictions of tropical cyclones have dramatically improved, significantly improved. But these extreme events, especially extreme rainfall and flooding, is becoming a big challenge. And so how do we deal with it? This is a big problem. And so I just want to say that recently in the COP meeting, India has also a Prime Minister, Honorable Prime Minister, Sri Narendra Modi ji. He has mentioned at the COP26 meeting in Glasgow, he has committed that India's ambitious carbon zero pledge by 2070. This is it's a very important thing, and but it's a big commitment as well. And of course, Prime Minister has also made a very powerful statement, one sun, one world, one grid at the COP20 summit, which says that we have to go for International Solar Alliance, go for renewable energies. That may be the option. And I will just play a short YouTube video, and with this I will conclude my talk.
Excellencies, नमस्कार। आज वन सन, वन वर्ल्ड, वन ग्रिड, इसके लॉन्च पर आप सभी का स्वागत है। वन सन, वन वर्ल्ड, वन ग्रिड की मेरी कई सालों पुरानी परिकल्पना को आज इंटरनेशनल सोलर अलायंस और यूके के ग्रीन ग्रिड इनिशिएटिव के पहल से एक ठोस रूप मिला है। एक्सेलेंसीज, इंडस्ट्रियल रिवॉल्यूशन को फॉसिल फ्यूल से ऊर्जा दी थी। फॉसिल फ्यूल्स के उपयोग से कई देश तो समृद्ध हुए, किंतु हमारी धरती, हमारा पर्यावरण निर्धन हो गए। फॉसिल फ्यूल्स की होड़ ने जियोपॉलिटिकल तनाव भी खड़े किए, लेकिन आज टेक्नोलॉजी ने हमें एक बेहतरीन विकल्प दिया है। एक्सेलेंसीज, हमारे यहां हजारों वर्ष पूर्व सूर्योपनिषद में कहा गया है, सूर्याद भवन्ति भूतानि सूर्येण पालिताति तु, अर्थात सब कुछ सूर्य से ही उत्पन्न हुआ है, सबकी ऊर्जा का स्रोत सूर्य ही है और सूर्य की ऊर्जा से ही सबका पालन होता है। पृथ्वी पर जब से जीवन उत्पन्न हुआ, तभी से सभी प्राणियों का जीवन चक्र, उनकी दिनचर्या सूर्य के उदय और अस्त से जुड़ी रही है। जब तक यह प्राकृतिक कनेक्शन बना रहा, तब तक हमारा प्लेनेट भी स्वस्थ रहा। लेकिन आधुनिक काल में मनुष्य ने सूर्य द्वारा स्थापित चक्र से आगे निकलने की होड़ में प्राकृतिक संतुलन को डिस्टर्ब किया और अपने पर्यावरण का बड़ा नुकसान भी कर लिया। अगर हमें फिर से प्रकृति के साथ संतुलित जीवन का संबंध स्थापित करना है, तो इसका रास्ता हमारे सूर्य से ही प्रकाशित होगा। मानवता के भविष्य को बचाने के लिए हमें फिर से सूरज के साथ चलना होगा। एक्सेलेंसीज, जितनी ऊर्जा पूरी मानव जाति साल भर में उपयोग करती है, उतनी ऊर्जा सूर्य 1 घंटे में धरती को देता है और यह अपार ऊर्जा पूरी तरह से क्लीन है, सस्टेनेबल है। चुनौती सिर्फ इतनी है कि सौर ऊर्जा दिन में ही उपलब्ध है और मौसम पर भी निर्भर है। वन सन, वन वर्ल्ड, वन ग्रिड इसी चुनौती का हल है। एक वर्ल्ड वाइड ग्रिड से क्लीन एनर्जी हर जगह हर समय मिल पाएगी। इससे स्टोरेज की आवश्यकता भी कम होगी और सोलर प्रोजेक्ट्स की वायबिलिटी भी बढ़ेगी। इस रचनात्मक पहल से कार्बन फुटप्रिंट और ऊर्जा की लागत को तो कम होगी ही, अलग अलग क्षेत्रों और देशों के बीच सहयोग का एक नया मार्ग भी खुलेगा। मुझे पूरा विश्वास है कि वन सन, वन वर्ल्ड, वन ग्रिड और ग्रीन ग्रिड इनिशिएटिव के सामंजस्य से एक संयुक्त और सुदृढ़ वैश्विक ग्रिड का विकास हो पाएगा। मैं आज ये भी जानकारी देना चाहता हूं कि हमारे स्पेस एजेंसी इसरो विश्व को एक सोलर कैलकुलेटर एप्लीकेशन देने जा रही है। इस कैलकुलेटर से सैटेलाइट डेटा के आधार पर विश्व की किसी भी जगह की सोलर पावर पोटेंशियल मापी जा सकेगी। यह एप्लीकेशन सोलर प्रोजेक्ट्स का लोकेशन डिसाइड करने में उपयोगी होगा एवं इससे वन सन, वन वर्ल्ड, वन ग्रिड को भी मजबूती मिलेगी। एक्सेलेंसी, एक बार फिर मैं इंटरनेशनल सोलर अलायंस का अभिनंदन करता हूं और मेरे मित्र बोरिस को उनके सहयोग के लिए बहुत बहुत धन्यवाद देता हूं। मैं सभी अन्य देश के लीडर्स की उपस्थिति के लिए भी उन सबका हृदय से आभार व्यक्त करता हूं। बहुत बहुत धन्यवाद।
So with that, I come to the end of my talk. Thank you all for your kind attention.
Thank you very much, sir. Thank you very much. You presented a really very elaborate review of the work done by Professor Manabe. That was so fascinating. We can imagine how much time you could have invested, by compiling all his work and papers and presenting a very interesting review of his work. I can see much appreciation of your work presented in this presentation. Many people are saying it was really great, and you have really invested yourself in bringing out this wonderful presentation on the work of Professor Manabe and how it could, help advance the area of weather and climate sciences, and with the recognition he's getting with Nobel Prize, and that will definitely attract more people to come into research in weather and climate sciences. That will help further advance the area. And you also succeeded in establishing a very nice connection between Professor Manabe and Indian climate community, and you also being so much involved with him. Thank you very much. And last you ended with the PM such a powerful speech, giving such an impression that what Professor Manabe found that this climate change is happening with human intervention, and how PM Narendra Modi is taking us to our future by using reliable, renewable solar energy. Before we could wind up, I would invite Professor Banerjee or Professor Montero from IISER Pune if they would like to say a few words.
Hello, everyone. Yes, I agree with Dr. Abhay. It was a really great talk. I think the fact that we started off with really fundamental papers, going through them and trying to understand the larger implications, and seeing how the sort of, though they may seem very simple experiments, their implications are profound. Even today's state-of-the-art models are not telling us so much in terms of the difference in global climate. And that just shows, I mean, both the kind of deep insight that Dr. Suki Manabe and the GFDL group had at that point in time. And also the fact that when you're looking at something as complicated as the climate system, it's good to focus on simple questions. And I think that is a very critical takeaway, especially for all the students who are attending this seminar. I think this was a very valuable walkthrough through some of the very important landmarks in climate modeling and climate science. So thanks again, Dr. Krishnan. I really enjoyed this talk myself.
Thank you, Abhijit. Thank you, Joy. And thank you, Partha. Thank you, everyone.
Thank you, Dr. Krishnan. Thank you, everyone. Thank you, viewers, for joining this presentation.
Before ending, you can ask
please.
to take a screenshot if everyone opens their camera. So, as for your record of this seminar.
Yeah, that would be very nice. Professor Banerjee, can you please?
Saab and everyone, whoever is present, they can just.
Professor Banerjee is also there?
Yeah. I'm here. I don't know if I'm visible. Actually, there is a question in the chat box. Do we have time to take it?
If there is a question, one or two, if Dr. Krishnan has time, you can take it.
Okay.
Yeah, sure.
Yeah,
I'm happy to.
Please go ahead.
There is one question from Dr. Madhuchandra Reddy. He's asking, how can we achieve climate change as PM told by 2070?
Yeah, so now there are some of these scenarios like very low emission scenarios. We have there's something called SSP 119, that is very low emission scenario in the AR6, CMIP 6, and there's a 126. So these emission scenarios, if you start analyzing, you can see how much the temperature is going to change, what is going to happen to the water cycle. So basically these scenarios have implemented some kind of a mitigation policy. When how the carbon dioxide is going to change in the future, how the methane emission, how the aerosols are going to change, what is the land use, land cover change. So they are kind of incorporating in these different scenarios. So if you look at these low emission scenarios, you will get an idea that is so the temperatures, still it says that limiting below 1.5 is going to be very hard in the next 20 years. We are definitely going to cross. But maybe if we go for very aggressive, rapid, and it should be sustained reduction, 2 degrees maybe we may be able to do, but still it's going to be a very, very big challenge. So the International Solar Alliance is a very big thinking, and if countries are going to do it aggressively, if they are going to pursue, there is a possibility. So we have to look forward to that hope. See, even with the COVID lockdown, the emissions came down, although the concentration did not change much, because these are very long-lived gas. They stay in the atmosphere for a very long time. And but the emission itself came down. Now, if you keep repeating this for, let us say, next 30-40 years, I'm not telling you should have COVID this one, but if you reduce the reduction of carbon dioxide, it's going to have an impact, definitely.
Yeah. Thank you, Dr. Krishnan. And there is another question we would like to take up. Rahul Kashyap is asking, what are the major climate change impacts on the land and biosphere?
Yeah, so major is the land warming is much faster than the ocean. I'm not able to give you the numbers right now, but the increase of temperature over land is higher because it warms at a faster rate. And so the impact is the heavy precipitation increase over land we can see. And over land areas, the droughts are going to become, especially in the Mediterranean region, the subtropical areas, Australia, Southwest Australia, Chile, and there are some of these pockets which are vulnerable to droughts. They are going to get stronger. So droughts also will become so both end of the spectrum. So regions which are getting rainfall, we will get more rainfall. So the same, the wet becomes wetter, dry becomes drier. There may be some exceptions, some areas that may be because of changes in the land surface process. It's much more complex, but by and large, it's kind of going to hold.
Yeah, and Rahul further wants to know what can be done to prevent further such changes.
Yeah, so prevention is prevention is see, the change is inevitable in terms, as I say, inevitable means because these are really long-lived gas and they are going to be there. The impact we are going to see in the coming decades. So the only thing is you can probably mitigate through some appropriate measures, increasing the vegetation cover. So the flooding, the impacts in terms of runoff, you can probably reduce. The impacts of flooding you can be reduced, improving the infrastructure, drainage systems. So these are things, and yeah, and the big thing is one sun, one world, one grid. So that in the long term is that's going to be important.
Yeah, that's a very strong statement. And we have another viewer, Raju. He says that lapse rate feedback is critical for greenhouse effect, as Professor Manabe and others have suggested. Now, moisture holding capacity increases as Earth warms up. So how would be lapse rate feedback respond now?
Yeah. So lapse rate, generally what we are finding with more increasing convection, the lapse rate is going to decrease. That's what is going to happen. So if that is going to decrease, so the atmosphere can become more stable, because the upper layers are going to get warmer compared to the lower layers, and so stability can increase. So there is a view that the tropical circulation intensity itself may weaken, and especially in closed loops like the Walker circulation, it can weaken. That's what is proposed. But it's a much more. It's not a very simple answer, but it also depends on clouds. When you are looking at a regional circulation, or so many other factors come into play, and what type of cloud systems you have, how the latent heating distribution is, how it affects the circulation, and so on. Yeah, but in general, I think the lapse rate will decrease.
Okay, yeah, and then we have some appreciation for you. VM DOS is saying that it was really nice to have a presentation ended with PM's, such a powerful speech, and he further wants to understand how would be understand how to avoid climate like Chennai, climate. I mean, he want to know climate change scenarios like Chennai floods, and Madhu also wants to know even Kerala. So we have seen extreme flooding in Chennai and Kerala. How to avoid such situations?
Yeah, now the problem is I didn't mention. See, the water vapor, we know now roughly when the temperature increases by 1 degree, water vapor in the atmosphere will increase by 7%. Okay, now we have already increased by 1 degree. Now it is globally it is 1.1 global mean temperature, but regionally when you see the anomalies are much larger. Okay, so the water vapor content in the atmosphere has increased. What that means is, and that is a big fuel for a low pressure system or a depression. If you are giving moisture, it is going to become stronger. The humidity in the atmosphere is the fuel for these systems or tropical cyclones. So they are going to get stronger, and so if they are going to get stronger, the precipitation amount intensity will also be higher. So heavy precipitation will increase at the same rate, that is 7% per degree warming, heavy precipitation. But global mean precipitation about 1 to 3%, they say, per degree warming, it's 1 to 3. But heavy precipitation will increase at the same rate as water vapor increase. So that is something very, very scary. The only thing is early warning systems have to be improved, and people, we can save lives, which is where, because for example, when you take the super cyclone Orissa 1999, a lot of people died at that time. But now you look at the recent examples, the numbers are very small. So the warning systems have improved, the evacuation measures are this one, and the track predictions are pretty good. So I think, and the state governments and other agencies, they're taking all the mitigation actions, evacuation and all those. So loss of lives, definitely there is a big progress in prediction skill have improved. Yeah, but then there are so many other impacts, like flooding and how to improve those, how to improve your water sewerage system, your drainage systems, how to avoid the water logging. These are all management issues also partly, and people have moved into vulnerable areas. We cannot blame them that, so that their exposure to risk is getting higher. So this is also another problem.
Yes.
Yeah.
Yeah. You're here presenting actually a very scary situation that with the increase of 1 degree, we are already in danger zone. And you also highlighted that, with the people moving in very danger zone are, even in the river basin areas where flooding, anytime it happens, it will be there. So people are moving there. And we'll wind up, sir, with one last question from Nirmal Raj. He's asking, to what extent cloud condensation nuclei vary with black carbon aerosols and sea salt aerosols?
Yeah, these are all very tough questions. What I'm telling is, after all this, we understand. See, carbon dioxide is a very well mixed gas. We are trying to now get some handle. We are coming out with some robust assessment. And now the aerosols, for example, they're highly variable in space and time. Okay. And now if you are talking about aerosols, what happens to the cloud microphysics, what kind of rain? I think it's very, very uncertain. And these are topics for research. It will require very, very careful studies to come out, because natural, as I said, natural variability is so much. If you want to say that this is what is the role of this is what the cloud microphysical effect of these aerosol, it's going to be very challenging. It will require very, very detailed and very systematic attribution experiments and demonstrate that. And it is possible, but people have to do that. And it will take, this is going to take time. That's what is my point. And the fingerprinting approach, what Hasselmann and other people they got, that's what they did, how to attribute the signal. This is due to human influence and whether it is due to natural variability. They have to do very systematically, and then only you can come to some conclusion.
Yeah. Thank you, Dr. Krishnan. There are a few more questions, but I think we are already exceeded time. So thank you for such a wonderful presentation and enlightening us about the work of Dr. Manabe. And he started with the climate change, with the carbon emissions, that is human activity. Now you are also suggesting, while concluding, that if we further want to get rid of this situation, we the humans are the cause and also the reason how we can stop it. Yeah. Thank you very much. Thank you everyone for joining this presentation.
Thank you.
And
thank you.
Thank you.
Thank you.
Thank you.
Thank you. Thank you, Joy. Thank you, Arga. Thank you. Thank you. Thank you, Joy. Thank you, Arga.